Welcome all. In this lecture, I will discuss about counting of irreducible representation using characters. In our earlier lectures, we have already discussed about the matrix representation, and there we have discussed that a block diagonal matrix can be constructed by using different irreducible representation, and we generally write those irreducible representation in the diagonal part of the matrix, and the dx, that is representative matrix, can be written in terms of the irreducible representation. This is the direct sum. This plus symbol is for the direct sum, and if there are m1 number of d1x matrix, d1x is basically a irreducible representation, d2x is also irreducible representation, and it appears m2 times, this d1x appears m1 times, and so on. So this equation we have already discussed before, and if we take trace on both sides, then the same equation can be written as chi of x is equal to m lambda chi lambda x, where chi lambda is the character corresponding to the element x. Now this equation can be slightly rearranged if you take help of the equation 29.14 and 29.15, which was already discussed in my just earlier lecture. But I am not going to discuss the detailed mathematical steps, but what we can show, that is m mu is equal to 1 by g sum over ci chi mu xi and chi xi. So this comes from two different representation. Chi is the character for two different representation, and they has been written in product form, and ci is the number of elements for the particular class concerned, and mu is the number of irreducible representation. So I will discuss one example where the meaning of this equation will be more clear to you. But one thing to note, that is this ambiguous formula can be given for each m lambda once the character set of D is known. When we know the character set of D, then we can use this formula, and it shows that for any particular group, two representations with the same characters are equivalent. So two representations with the same characters are equivalent, and this strongly suggests something that can be shown. The number of irreducible representation is equal to the number of conjugacy classes. I am again repeating because this is very important, and this particular formula will be used in the subsequent lectures. That is, the number of irreducible representations is equal to number of conjugacy classes. But here we are not going to derive this, but we have to just note down this issue, that is the number of irreducible representation is equal to the number of conjugacy classes. Now let us come to an example where above discussion will be clear to you. Suppose we are considering the group 3m, and we have the basis functions x square, y square and xy, and suppose we are going to find the irreducible representation for this particular set of basis function. We first note that although these functions are not orthogonal, but they form a basis set for a representation, since they are linearly independent quadratic forms in x and y, and any other quadratic form can be written in terms of them. For example, suppose x plus y whole square is equal to x square plus y square plus 2xy. Similarly, we can also form x minus y whole square with this particular basis function. We must establish how they transform under the symmetry operations of group 3m. So let us now investigate, that is how this particular basis functions transform under any operation of the group elements 3m. We need to do so only for a representative element of each conjugacy class. We know that for the group 3m there are three classes, and we can take only one element from each class. So let us start from the identity element I. Now for the identity element I, the representative matrix Di will contain 3 by 3 unit matrix, as there are total 3 classes. So the matrix element will be 3 by 3 unit matrix. The second class contains the rotations A and B. We know the second class contains rotation A and B, where A and B are related by similarity transformation. So we can consider just only one element. So if we find dA, that is representation of dA, then dB will be same. Now how to find dA? So for this we have to check that is how this basis function transforms under the operation under the basically rotation operation A. But this operation we have already discussed in our earlier lecture, that is if we apply the rotation operation, then x changes as minus half x plus root 3 by 2 y, and y changes as minus root 3 by 2 x minus half into y. So if x changes in this way, so square of x will be this, from this we can write square of y will be this, and product of x and y will be this. Now as we have found out x square, y square and xy, and our basis functions are x square, y square and xy, so we can find the matrix dA. How to find? Because you see dA, we are writing dA by looking at the coefficients of x square, xy and y square, because you see that if we consider the coefficients of x square, so in the first case, that is this one is 1 by 4, then 3 by 4, then root 3 by 4. You see we have written 1 by 4, 3 by 4 and root 3 by 4. Similarly, by looking at the coefficients of xy and y square, we have written other columns. So in this way we can construct dA, and if you just write the basis functions x square and y square and xy just right side, and if you multiply, then you can obtain these particular values. So we can obtain dA matrix from these equations. Similarly, for the third class, in which there are total 3 elements C, D and E, and they are basically the reflection elements, we can take any one of the elements. Suppose we choose C, because under C only x changes sign, x becomes minus x and y is unchanged. So x square and y square, they will remain unchanged, and xy will be changed, because x is square of x square and minus x square is same, y is unchanged, and as x changes sign, xy will be changed. So this can be reflected by this matrix. You see, if you write x square and y square and xy here and multiply, you will obtain these values only, because for x square we have written 1 and 1 to indicate there is no change of sign, and for the xy there is minus 1. So in this way we have obtained 3 representation. This is di, this is dc and da, and trace of the matrices are 3. For I3 trace is 3, for DC the trace is 1, and for DA the trace is 0. So these are the traces of the matrix. Now you see the table here, that is the corrected table, and for D, that is the representation that we have just constructed, we have written the trace here, that is 3 and then 0 then 1, 3 0 1. Now we will use the formula 29.18, and we will use we use this formula to check, that is how many times a particular representation is used for the construction of D. So you look at the formula again. So this formula is A mu, that is the number of irreducible representation, that is equal to 1 by G. G is the order of the group, that is 6. Then Ci is the number of elements in the class, and this is the product between the two representations. So suppose you are considering MA, then 1 by 6, 6 is the number of group elements. Then as Ci is multiplied, Ci is the number of elements in the class, so this will be 1, 2 and 3 respectively. Now you see, that is what is the product here actually. You see the equation again. So this is the product between the characters. So we are considering A1 representation, so mu will be A1, and we have to multiplying the representation that we have right now obtained. So the multiplication will be with characters. For example, suppose if you consider A1, then product will be 1 into 3, then 1 into 0, then 1 into 1. So you check 1 into 3, 1 into 0 and 1 into 1. Ultimately you are obtaining 1. If you consider A2, so other things will be same, just product will be like this, that is if you consider A2, then 1 into 3, then 1 into 0, then minus 1 into 1. So you are obtaining 0, and similarly for AME you are obtaining 1. Now what is the meaning of that particular result? So A1 and E appear once each in the reduction of D. This is the meaning actually. That is, A1 representation and E representation appear once when we have constructed the matrix D, but A2 does not appear in that particular matrix. So this is the meaning actually. So here we have used the result of the equation 29.18. And what is the meaning of that? The meaning is this, that is the combination x square plus y square and that transforms as a one dimensional irreducible representation, and the pair x square minus y square comma 2xy that forms a basis of the two dimensional representation E. Actually, when we have constructed the table, character table, there we have shown that. Let us look at the character table again, then it will be more clear to you. You see that in the character table we have written some particular functions just right side of the particular representation. For example, you see that is x square plus y square. X square plus y square has been written for A1. So our basis functions are x square, xy and y square. So x square plus y square, that function is applicable to A1. Again you see that is the combination of x square, y square and xy. For example, this function x square minus y square comma 2xy, that has been written here for the irreducible representation E. So that is why A1 and E is used here, but for A2 only RZ is there. That is why A2 has not been used for construction of the matrix D, where the basis functions are x square, xy and y square. So this result supports the table that we have described earlier. So I think you have discussed the issues which has been discussed in this lecture. I hope you have understood it, and for further understanding I request you to go through the textbook of Riley, Hobson and Benz, and I also thank you for listening the lecture.